In this week, AI. In this week, we will talk about the convolutional neural network. Just remember the previous lesson. In the previous lesson, we have talked about the neural network structure, but in the feed-forward structure, right? In this establishment, we design the input layer and add the hidden layer, and after that we add the output layer, right? But in the convolutional layer, we have different properties, just like this one. In order to understand this process, we need to give some examples in here. Suppose that we have data like this one. For example, x1, x2, x3, x4, blah blah blah, and xn. Okay, and also we can create this line in order to write the whole data in order. Okay, so for example, first data 1, 2, 3, 3, and 99, and 4, 5, 6, blah blah blah, 1, 2, 3. Okay, this data is distributed just like this one, and also 1, 2, 3, 3, 99, and 4, 21, and 21, 4. Okay, and also this is the 10, 1, 3, 3, 95, 4, 12, 1, 4, 3, 2. Okay, and also this goes on just like this one, 3, 3, and 10, and 9, and 4, and 4, or this is the 3, 3. Okay, in this case we have the data up to the xn variable, or the state, or the vectors. Okay, so in the standard feed-forward neural network, we have this data in the process of this one, right? For example, if we are using this data, we have the n input, and so after that we have the hidden layers in here, and also we have the one output, maybe. And so this n input generates the n different data, or n different axes. But at each case we utilize sequentially the first one, and second one, and third one, and fourth one, 5, 6, and blah blah blah, up to up to m data. Okay, in the feed-forward neural network, we feed all the data in terms of in terms of this sequential layer, x1, x2, x3, x4, and after that we will forward to the second column in here. But if we are using the standard NN application, we can identify the y, or classifying the y in here for a given this first data, or second data, and third data. However, in the relation between these matrices, we have some specific feature to analyze the 2D form. Okay, and so in this form we have one dimension, and this one dimension contains the n different data. But just see or look at to the graph. For example, we have the same pattern in here, just like this one, but we need to evaluate these two patterns at the same time, or we need to evaluate this pattern at the same time in here. Okay, because if you are using the 2D dimension in here, just see that everything is given in the tree, and which means that this is meaningful feature, but we don't know yet, right? And so if we are using this property, maybe we can't identify 1D data, but 2D data may be meaningful. Just like this one. If we are utilizing both tree, and so we can generate the meaningful output in here. Or if we are utilize the whole 99 carrying the pattern in here, and also this is the 4 and 4 and 4, we can generate some grid data in here. And so this is meaningful M1, and also this is meaningful M2, right? But in the 1D dimensional, we may not catch this property in here. And so the main feature is that the grid data in more dimension may be meaningful. Okay? So in normal case, we analyze whole normal case contains to the horizontal data, but we need to analyze both horizontal and vertical data at the same time. And also we need to find some patterns maybe contained in the 2D data, not the 1D one. Okay? And so in this case, we need to evaluate the 2D or 3D or 4D data in order to capture the features of these data distributions in here. Okay? For example, maybe we have the ECG data just like this one, electrocardiogram data, which is the electrical representation of the heart signals. Okay? And so we have the atrial electrical activation, and this is the ventricular activation, and the ventricular repolarization is represented based on the 1D data. But this data is time dependent data. Which means that if we have the ECG signal or array, we have I to I plus W. This is the window size. But this is 1D data. Okay? But instead of using only this one, we can generate the left ventricular volume or pressure change data is given in here. Okay? And so maybe this data cannot be identified as the contraction beginning. But if we are using these two data, we have just kind of this information. For example, 1, 1, 1, and 2, and minus 1, and 10, and minus 1, and 0, 0, 5, 0. This is the ECG pattern. Okay? And so we can analyze the window-based techniques in order to represent the whole terms in the standard neural network applications. But if you are using this data also, for example, 50, 50, 50, and after that we remove the whole data in here, decreasing to the 10 and minus 1 and 0, 2, 3, 4, 5 and 10, 10, and goes on this kind of data. Okay? 10 and 10. And so maybe this is not enough to identify the properties of the heart condition. But if you are using or utilize this pattern, just like this one, this is 3 times 3 matrices, or we can analyze 2 times 2 matrices, or in a common point, we can analyze a great data point in here. Maybe this is more meaningful to the what to analyze or characterize our output in order to what? In order to classify our hard conditions. Okay? And so this is the advantage of the what of the great data utilization in the what in the neural network application. In the standard neural network application, we have always a 1D data. At the same time, one data is processed, even if we have the n inputs. But in this case, we apply the data processing on the what horizontal and the vertical at the same time. This is the advantage of the what pattern or the great data utilization. We can create relation between the Windows-based data and the difference feature with one variable. Okay? This is the pre-processing phase for the what? For the neural network applications. And so, how about this one? For example, we have the many mathematical methods in here. Suppose that we have a signal. So, for example, this is the first signal. This signal is the what is calling to the what? The GT. Okay? And in the second signals, and so maybe this one, for example, the GT square. Okay? And so in the third one, maybe we can assign to the what, to the new data, is the absolute values of the what? The GT. Or we can assign or apply the fast Fourier transform in here, just like this one. And so FFT GT is given in here. And also we can add another filter in here. This one, and this one, and this one. This is also wavelet filter or GT data. Okay? And so this creating a pattern in one form, but we have relation to the each other. Okay? And also Y or GT can be assigned, for example, the sin t, sinus t. In here we have 1D data, but if we add another feature by taking to what? The square form, absolute form, or fast Fourier form, or wavelet transform of the GT signal, we can create to the what? To the, for example, 5-dimensional data. 1, 2, 3, 4. Okay? And so we can also generate the what? The window in here, just like this one. For example, this is the 1, 2, 1, 0, 1, or 2.2 and 1.2 and 5, 6, 7, minus 1, 2, minus 1, 0, 1, and also 2, 2, 2, 1, 0, or 1, 10, 1, 0, 0. This is the arbitrary number which is given in here. But in the first place, if we are using the only standard neural network application, this GT is just classified or regressed based on this data. Standard and an application. But if we are using the what? Some great pattern, we can analyze these three kind of data at the same time, or these three kind of data at the same time. And so this is called the great data contribution. Okay? And so we may have more analyzed or the pattern which is given in here, just like this one. Okay? In the standard signal amplification, we can use this property in order to what? In order to enrich our data process on the what? On the input layer. And so, what's the relation between the real life applications? For example, we can write another example in here, x2. Okay? And so, suppose that we have, for example, we have a picture in here just like this one. Okay? And also we have the what? The cat. This is Nazife. This is the mechatronic cat. Okay? This is so angry. But how can we define the nazife here? First of all, this is calling the cat, okay? And so we can conclude that there is no meaning in here in each row. For example, 224 pixel image, 224 and 224 pixel image, which is given here. But if I only look to what the one row in here and row, and so we don't have the meaningful data. But maybe we have only interested in head, just like this one. If you are looking to this pattern, how this pattern is meaningful right now, because if you are giving the only n row data to the human, not the AI one, you cannot easily identify this as a cat. But if you are looking at the x and y axis at the same time in here in the math, and so this is meaningful, okay? And so in the artificial intelligence, this is called the convolutional neural network and is mainly used to build a relation of tensor with higher dimension, guys. But ANN or standard feed-forward neural network cannot do that in a manner easily, okay? It can, but sometimes, okay? And so this CNN is dealt with the tensor with a high dimension. And so what is the tensor? Tensor is the grid data, guys. Grid data. But maybe this tensor is counted 3, 3, 3 and 3. Maybe this one. Maybe the another one. Maybe the 3D or 2D. It doesn't matter. This is called the tensor, okay? And so this is the advantage of the utilization of the convolutional neural network, okay? In the convolutional neural network, we can analyze at the same time to the vertical and horizontal process, or the row and column are processed at the same time by using this neural network with the help of the convolutional layer, pooling layer, or the value layer, or something like that. We will talk about it, okay? And so, any question? Okay. If there is no question, and so we will continue with the CNN and its layers, okay? Its layers. We have 9 main layers, or the different properties in its structure, okay? First of all, the first one is the input layer, okay? And so input layer contains the raw input data, guys, okay? Typically image or the tensor, for example 2, 4, 10, 4. This is a tensor, but also we can use the 100 times 100 pixels image can be given in here, okay? In the second layer, we have a special layer, convolutional layer, okay? This convolutional layer possesses the specific function, kernel function. This is specific matrix to analyze or combine the feature of the horizontal and the vertical properties of a given image, okay? And so, but we have a different property. This convolutional layer has the property of the learnable filters, okay, to input data, okay. And so how we can do that? This is the kernel function core or matrices, which is given in here, is trained based on some kind of the backpropagation algorithm and convolved. Convolved with image to generate to the what? To different different feature map, okay. So in order to combine the features of the horizontal and the vertical axis property for a given matrix or the image or the tensors, we need to utilize a convolutional layer. Otherwise, we cannot combine this property, and which is called what? Standard neural network application. Also, just like in the standard neural network application, we have an activation layers, guys, okay? In the activation layer, we create to the what? Nonlinearity or the hard nonlinearity. In order to what? In order to model to do anything in a what? In an independent feature. And this helping to the what? To the complex nonlinear pattern, okay? Because it creates the hard nonlinearity in here. And the output is still a set of feature map, okay. And this is not enough, because the activation layer is just kind of using the sigmoid function or the ReLU function or Leaky ReLU function or tan H function. And it creates the nonlinearity to create the what? The complex nonlinear patterns in this case, okay? And so, in the fourth place, we need to give the pooling layer, okay? In the pooling layer, if we have the data, for example, 1000 times 2000 pixels, okay? And so this is a 3 byte, and also this multiplication is a 2 million bytes, okay? And this is so huge to what? To analyze to what are patterns. But this pooling layer downsampling operation to get local maximum values, okay? For example, if we have this kind of 102, and so the meaningful data is the what? Maybe this one, 100. Okay, the other ones is unnecessary patterns in here, okay. And also this reduce to what? To overfitting or overtraining. Otherwise, our CNN network or the neural network can imitate the feature of the for a given data, not to learn one, okay? In Turkish, taklit etmek, okay? So, in the fifth, we have the special layer, fully connected layer, okay? Fully connected layer is just like of the what? The standard and an hidden layer. And so the every node is connected to the other one, okay. And so classification or regression is done in here, just like the standard neural network applications. Okay, but you must remember that we have always deal with up to the pooling layer with the 2D data. In the fully connected layer, we need to convert 2D data into the 1D. Okay, and so the whole data must be flattening. In here. Okay. And so in the 6th layer we can build the output layer. Okay, the output layer just like which is given in the standard end, but we have a different properties in here. The final prediction is given in here with the specific neurons. For example, softmax or sigmoid or tanh or linear. Okay, that one. And also we have some special properties or the layer, normalization layer. We will talk about the normalization layer in the next lessons, but the normalization layer is called the batch normalization in the literature, which is used to stabilize to the what and speed up training fast. Okay, we have the many data in here. Okay, and so this normalization is based on the what 0 to 1 or mu and standard deviation values of the what for a given data set in here. And so this removes internal covariance shifting, because we have maybe some great noisy data in here, but if we normalize the whole data with in terms of what the mean or standard deviation values or 0 to 1, and so we can remove this property, and so we can stabilize our training fast in this case. Also we can create the what dropout layer in here. What's dropout? Dropout is deactivate a fraction of neurons to reduce overfitting. Okay? Deactivate. I'm sorry. And so how can you do that? For example, if the dropout layer number is equals to 0.1, and so if the neuron possesses the 0.01 output, and so this is cancelled and the connection is removed. Okay, and also finally we have to what to 9 in here, though we have the flatten layers. This flatten layers converting multi-dimensional features map into a flat vector before fully connected layer. Okay, these 9 parameters are the what are the basic properties for creating the convolutional neural network. Okay, but we need to deeply analyze these properties in here. First of all, we need to begin with the what the convolutional layer. Okay, in the convolutional layer, suppose that we have an image just like this one. For example, we have a portrait like this one, and so we have a human in here. So And also we need to obtain the regional feature is in here. This is the regional feature. But how we can do that? If we have utilized to what the convolutional layer. This is our purpose. And so if I want to obtain the information which is given in here, just like this one, and so we need to apply the convolutional operator. But what is convolution? Convolution is a similarity rate between two functions or tensors in this case, or matrix, right? And so how we can define this convolution? Cij, which is equal to this the index, and so summation operator just like this one, m, n, and I is the picture, I minus m, j minus n, convolution operator f, m, n. Okay, and so in this case we possess what the discrete values of these terms. This is the n, and so this is the input, but this is the filter one, or the impulse response of the R filter. Okay, and so we can use this property, and so we can generating different pattern, changing to the what? Filter, right? Because each convolution creates what the different properties of this hat. Okay? And so how we can do that? In the standard notations we have in CNN, we have several key parameters, like for example number of filters, which is how many different filters are used to catch different features. For example, if we use the one filter, and so we can train the one pattern, but if we use the 10 number of 10 filters, and so we can create the 10 different features of the R picture, and so we can enrich the R image into the 10 image. For example, if I put or fed into this CNN one picture, and so if we are using the 10 filters, and so we can generate 10 more different features. We can enrich the input data by using this filter. Also we have a filter size. Okay, this is called the kernel size of a filter. Okay, that determines the effective area. Okay, and also we can derive the stride, the step size, at which the filter moved across the input. Also we have a padding. This padding, additional pixel. And so this is just a word, but if I draw this image just like this one, for example, if I put the 5 times 5 matrix, this is called the kernel. Okay, And so at each case, the containing or the crossing to the what the internal values of this pixel, we can convolve it. Okay, and so the stride is the step size in here. For example, if I choose the 10 stride, and so in the second place, this pixel is to what is going to what the 10 pixel to the right. Okay, and also we can define what the padding, additional pixel in here, in order to what, in order to collect the whole the information of the what the last row or column values of these terms. Okay, so what about this one? We have one more data, the filters. Okay, we have some special filter, the grid parameters. We will solve this example in the last session. Okay, but this for kernel we can use specialized matrix notations to be learned in the what during training. Okay, for example, we can apply to the what to the edge detection filter or sharpening filter, or maybe we can convert the R picture into the grayscale by using the sum filter, or we can detect or train to the what to the filters to what to catch the eye or face. Okay, and also we should add the activation function at the end of these filters to create to the what hard nonlinearity, guys. Okay, and so if this is the soft right now, don't worry, because we will build the PyTorch example about it. Okay, hard nonlinearity. After that, we should give the what the max and the average pooling layer. In order to define this property, we have to what max pooling, and this max pooling is utilized for the what the most active parts. I'm sorry, parts can be catched. For example, if we have the data distribution just like that, 50, 1, 2, 5, and so most active part is 1, and so this is the what 4 times 2 times 2 is converting into the what the 1 times 1 for the what for the max region. And so local region for smooth transition can be used in here. For example, in order to use this, the local transition can be catched. But how we can define it? First of all, we can build the bottom matrices in here just like this one, and so 50, 100, 200, 100. Okay, and so 1, 2, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, and so if I apply the max pooling, and so we can detect the what these parameters in here, and so maybe this is the H or the local transition point for the what for this process. And also we can apply the average pooling, and it's mainly used to what the robustness to variation. Okay, maybe you have the noisy signal or noisy inputs or noisy emits, and so removing noise in here. For example, if we have the data just like that, 5, 4, 3, but one term is 50, and so if I apply the average pooling, and so this reduces into the what, maybe for example the 7, 7, 8, 8, for example, and so smoothing the whole the signal based on this information. And so the higher peaks can be reduced by using these terms just like this. Okay, and after that, the last one, fully connected layer. If we have any, for example, 10 convolutional layers, 2 pooling, and so if we have input signal 10 times 10 image, for example, multiply with the 10, this is generates what? The 1 10 times 10 times 10. Okay, and so after 2 pooling, this reduces to 10 times 10 times 9, maybe, or 8. And so the final output is the what? 800 data, but the first output is 100, and so this enrich the data set by using different filter, and so we can define the R filters or learn to the filters to what? To classify the R image based on this information. Okay, this is the huge advantage to utilize to the bot to convolutional layer network. Based on this information, we can increase the R input dataset, and so this dataset can be used to what? Classify more accurately. And so how we can do that? First of all, we need to flatten all the data, just like this one. And so each pixel is organized as to what? As a one row. Each pixel. This is the 0, this is the 8 values of this pixel. And after that we add the neurons just like to what? To neural network, feed-forward neural network. And also we can add to what? The softmax layer or sigmoid function. And also we can decide to the what? The output 2 and output 1. Okay, and so we can add the softmax layer to generate the most probable choice which is given in here. Okay, this is the basis of the what? Of the R properties for a given the CNN structure. Okay, so in the last place we need to talk about the optimization function and the methods. We need to compare it. First of all, we will compare to the what? To the two methods in here. First of all, stochastic gradient descent. This is the basis of the what? The backpropagation algorithm, SGD. And also we have the ADAM optimizer, adaptive moment estimation. Okay, this is the what? Optimization technique to what? To learn the whole the coefficients for a given data set in the what? In the CNN structure. Okay, so first of all we need to give the advantage. First of all we need to write, because the stochastic gradient is the simple. Okay, and also this has a low memory requirement. Okay, just only utilize what? The gradient in here, and so we can add the whole the terms based on this one, and it's good, generating good results for large data set for batch processing. Okay, this is important. And also the ADAM is fast converging algorithm, and also adaptive learning rate, which is the basis for the what? For the learning process. This is so important, especially for the control application, for the reinforcement learning. And also this is robust. Okay, this is the advantage of the what? The ADAM optimizer. And also we have a disadvantage in here, just like this one. This is slow convergence, and also sensitive to learning rate, because it's not adaptive, or the momentum term cannot be added in here, or it's not feasible. And so this is sensitive to what? To hyperparameters. And so we need to apply the hyperparameter optimization for the what? For the Atom optimizer. And also the memory requirements are huge for training phase, not the application one. Okay? And also how we can classify these terms in here. The application can be given to what? To this one. This is used the classical image classification task, okay, or regression one. But the Atom optimizer is more useful to the what? To generative models and also LLM, large language models, guys. Okay. So this is the optimization method. This is the learning rule to what? To optimize our algorithm. But we have also 2 for loss function. Mainly we utilize to what? Root mean square error. I'm sorry. Root mean square error, RMSE, and also we have the cross entropy loss. This is called the binary, but it has a few huge advantage. Okay, first of all, we need to give the advantage of these algorithms, advantage, and so suitable for regression because it's the square root of the what? Error. Continuous values, okay, and so this is interpretable. Okay, this is more easily interpretable in terms of the what? In terms of the meaning, or to make the meaningful data. And so cross entropy is ideal for classification, not the regression one. Okay, and also it's discriminative, which means that either it generates 1 and 0 is given in here. Okay, and so it's more discriminative. For the disadvantage, we need to write to the what? It's sensitive to the noise, and also not for classification, or it's hard to find out, and so no regression data. Okay, and also we need to give the what? Application session for these terms. For example, this is the more like the prediction, estimation of continuous values. Okay, and also this is the image classification, sentiment analysis, and text recognition. Okay, because it's defined as the binary coding. Okay, and so if you are using the binary coding, the cross entropy is more useful to what? To analyze the whole data based on these informations, guys. Okay, so this is the last topic about the what? About the our text lesson. Okay, and so we need to move to the what? To the our example session right now. Okay, any question? Any question? so just give me a second, guys. Okay, first of all we need to open to what, to our internet, and so the code, open with code, and so I'm sharing my page just like this one. Okay, and so could you see my page right now? Okay, and so first of all we have this Detaylı. Okay, this picture are the main course of this lesson, and so we will apply some features or the filters to this picture, and after that we will obtain to the convolutional feature, pooling feature, or the layer feature, fully connected layer feature, normalization feature, and the output layer features. But first of all, in order to understand how we can use the convolutional filter, we must write to the week 4, for example, cone filter types. Okay, what's the predefined types, guys? Okay, and so in order to do that, import CV2. Open CV library is utilized in here, and also import numpy as mp should be given in here, and import matplotlib dot pyplot as plt should be added in here. Okay, so this is mainly for the the OpenCV applications. Okay, and so first of all, image can be obtained the CV2 body with the imret function. Okay, in order to import the matrix or the tensor feature of this matrix, we need to utilize the imret function, and after that the image maybe have this different size for a given dataset, but we need to resize whole the image based on based on this tuple 224 and 224. Okay, so also we can apply or define some function def apply convolution function, which is given here the image kernel input image and kernel. Okay, and so the output image can be given by CV2 filter 2D and input image -1 and kernel. Okay, and after that we need to return these values, and this CV2 filter 2D is a convolutional pattern for our algorithm. And so in order to analyze these features, and so you can easily check the parameters of these terms of just like this one, the matlag def -1 and kernel, the standard kernel is in here. Okay, so how we can define the different kernels in here? Define, for example, sharpening and blurring kernel matrices. Okay, and so the sharpen kernel is defined with the MP array, and so this is so standard, and so I need to copy all of these terms in here. Okay, sharpen kernel is defined 0 -1 0 -1 5 -1 and 0 -1 0, which means that this is the R kernel, and so at each case our image is processed or applied to convolve this sharpen kernel with with the basis image, and so this convolution generates the sharpening kernel. Okay, and so also blur kernel can be defined with MP array, and also we should give 1 to 1, and after that 2 for 2, and after that 1 to 1. Okay, and after that 1 divided by 16. This is the normalization rate of the for blur kernel, and H detection kernel must also be given here, MP array. Okay, so we can copy all of these terms in here just like this one. And so the first one is the what is 0 minus 1, and so there's 0 4 and this one. Okay, after that we need to apply sharpening and blurring pattern, and sharpened image can be given by apply convolution with what, with the image, but in this case sharpen kernel must be given in here because this is the sharpening kernel, and so this is returns what the output image for a given the filter type in here. Okay, and also blurred image, and so this is the blur kernel, and also H image can be built with this case. Okay, H detection kernel. After that we need to plot the figure in here in order to show the results with what 12 and 4, and plt dot subplot, which is given 1 for 1, and so the plt imshow cv2 cvt color image and cv2 color bgr to RGB. Okay, this is the feature of the what the different color techniques in here. Okay, and also plt title, this is the original image. Okay, so after that we need to copy all of these terms, but right now the sharpened image, which is given here, the color BGR to RGB should be given here, but this is the sharp, and also this is the 2, and also 3 and 4 should be given in here just like this one. This is subplot, I'm sorry. Okay, and so this is the blurred image, this is the H image. Okay, this is blur, this is the H. So after that we need to show the plot show, and so if I run this code, and then we will have, see, in the original picture we have the 224 data, 224 data. In the sharp image, just see that this more sharpened, this is blur, and so this is the edge image. Just see that this is the aging features in here. Could you see that? We can identify the age of these terms, but how we can change the R parameters? For example, the age detection, maybe we can utilize 20 values in here, just like this one. And so just see that the output of this image is changed, right? Okay, but there's no image in here, and so how we can change the what to 10? Okay, and so see, in the 10 maybe we may have the what, the age, but the more blurring image in here gives in here. Okay, and so if I put the 2 in here just like this one, so in the 2 we have the only dots in here. Okay, and so this is the 4, but maybe this can be assigned to the 6 right now, and so this is not useful for our image. Okay, and so maybe this is the 4, right? This converts to the what, to the R image, to the what, to generate of the what, age values. What about this one? If this is 8, and also, or if we multiply the 2, hold the terms in here, and so see that the R generation is what is more clear. But what about this one? If I choose the 5, so the more construct in is given in here, right? So maybe this is special filter to what, to obtain the age detection. But what about this one? If I sharpen this one, this is the 5, or if I choose to what divide by the 4, this blur kernel in here, this blur image is not a blur right now because the total energy is changed right now, because the whole term is collected with what 1 2 1 4 and 8. Okay, 4 4 4 16 value divided by 16 is a normalization value of the blur kernel, right? And so the last one, our general purpose, our kernel maybe defined just like this one. Maybe, for example, 1 2 3 4 1 and 2 and 2 1 minus 1. Our kernel is defined just like this one, and so this is also our image. Okay, and so our kernel is redefined in here based on these informations, and so 5 5 5 and 5, and so our kernel is given in here. Our image is convolved in here, the R image. So if I run this code, and then the R image, this should be 5. Our image is look like this one. But what about this? If I choose to choose to 1 and 0 and 0 and 0, maybe this is the case of the R kernel, and so it looks like the different image. Okay, and so 1 3 1, maybe if I choose this one, and so this is more different image. But the main point is that how we can find to calculate or to find the best coefficients to identify the age or the sum properties or the sum hat values in here. This is the topic of the training convolutional neural network. These kernels is trained, these coefficients are trained in the convolutional neural network layers. Okay, after that, just like this one, the blur kernel, edge detection kernel or sharpen kernel can be generated for our purpose to detect, for example, the hat. Okay, maybe this is the hat kernel, but in order to create hat kernel, maybe we must multiply 10, and so these coefficients so trained or find out to generate our basic properties in here. See? But how we can learn this structure, and so we need to utilize or build the convolutional pooling or fully connected layer in order to regenerate the R patterns based on this information. This is called the CNN training fast based on stochastic gradient descent or the Adam optimizer, guys. Okay, any question? Okay.